Hi guys, I hope you're enjoying your holidays. Just to let you know, before you start watching this video, you should really download the holiday video PowerPoint, which will be in my Dropbox under Unit 4 on Edmodo. Okay, so in this video, I'm going to finish off a little bit about equilibrium, whatever we didn't get done in class, and then go through some practical applications of equilibrium, so how to answer exam type of questions. Okay, so under the first part, what I'm going to be doing is talking about the equilibrium constant, K, and tell you a little bit about its purpose and, why we use it and things like that. Okay, so the equilibrium constant. Now, why did they want to identify a constant? Okay, there are many applications from learning about K, but basically the equilibrium constant tells us, a relationship between the concentrations of our reactants and products at equilibrium. It's a relationship between them. Now, K is specific for the type of reaction and a particular temperature. So the relation between the concentrations of reactants and products is going to be specific for the type of reaction, obviously, whether it's 1, whether it's 10 to the power of 4, whether it's 10 to the power of -4, it will be specific for that type of reaction. Okay? At equilibrium, the concentrations of our reactants and products will be equal to K for a particular temperature. So whether it be our example of ammonia, the creation of ammonia, whether it be nitrogen dioxide being converted into N2O4, these will have different K values. K equals X, K equals Y. They're different because they're different reactions. This one at 10 degrees Celsius will be different, will have a different K, and let's say that this one's at 50 degrees Celsius, it will have a different K value because, as I said, K is specific for temperature. Okay, so the purpose of K. K has a number of purposes. We can use a known K to determine if our reaction mixture is at equilibrium. Okay, another thing K can be used is if we know our reaction is at equilibrium and know the concentration of, say, our products or reactants only, we can work out unknown concentrations, say for our reactants, if we know the K. K can determine unknown concs. Okay, so there are a number of useful applications of K. How do we determine K? Okay, in an exam situation, there's no special way to determine K. K can only be determined if we K can be determined K can be determined if we know the equilibrium concentrations of our reactants and products. And then we sub it into the generalized formula of WA plus XB produces YC plus ZD. We can work out K as the concentration of our products to the power of their coefficients divided by the concentration of our reactants also to the power of their coefficients. This needs to be obviously for your reaction. So for example, if you don't have two reactants, you only put one in. If the coefficient is 1, it's to the power of 1. You don't need to write that. So things like that. Okay. So K is a constant which is specific for a particular reaction and for a particular temperature. So basically, K for a particular reaction only depends on temp. It doesn't matter about initial amounts, concentrations, pressures, catalyst. K doesn't change. So if we add some, this has reached equilibrium, it has a particular K. Now we add some A, it will shift it to readjust to equal K again. Okay, we're going to talk about that when we come back. Now, basically, we're going to continue on with the equilibrium law, which is K. As I said, K is specific for the reaction quoted. So let's have a couple of examples. We can have this being converted into this. For this reaction, K equals NO2 to the power of 2 divided by N2O4 to the power of 1. Write that in. Just the sum of mass. So that's example 1. Example 2, we know that this is a reversible reaction. So K will be different. In other words, K will be the inverse of the K that I wrote just above. So these two are actually mathematically related. Let's call this K1 and K2. How is K1 and K2 related? Well, when we reverse the reaction, K is inverse. So in other words, K2 equals 1 over K1. So when we reverse it, K is 1 over K1. So let's say K1 equals 2. We know that as a value. K2 equals 1 over 2 or a half. You can imagine that if K1 equals 2, then the concentration of our products is 2, then this might be 1. Well, it has to be 1 to fulfill that. We simply, follow the rule. So we flip it, it's 1 over 2. So that'll help. For example, if they tell you what the K is of a forward reaction, And then they ask you, what's the K of the first reaction? Well, it is the inverse, 1 over K. Okay. Let's see another mathematical relationship. Now, we have these ones, okay, that we've just worked out before. Let's say that we have the reaction a half N2O4 gas is converted into NO2 gas. This K would equal NO2 to the power of nothing, to the power of 1, sorry, and then divided by the concentration to the power of a half. Okay? When this is similar to delta H, how that changes, okay? So it's very specific for the type of reaction, how many moles of this, how many moles of this. When we halve the coefficient, K equals the square root of K. Sorry, let's just say that we call this K3. K3 equals the square root of K1. Let's take a minute to process that. K1 equals 2. And let's say that we follow on with these concentrations. So K3, we'll have a concentration of the square root of 2 over the square root of 1 equals the square root of 2. All right. So when we double the coefficient, we have to square K. So in other words, K1 equals K3 squared. Does that make sense? Okay. Now, we're going to do a couple of examples. The first example we're going to do, people got that with you? Oops. Now this is talking about the rates of the forward, and the reverse reactions at equilibrium. All right, so the question says, when 2-propanol reacts to form an equilibrium mixture with propanone and hydrogen, which one of the following best represent how the rates of the forward and back reactions change over time? Now let's identify the reaction, the forward reaction. It says, when 2-propanol reacts to form an equilibrium mixture with propanone and hydrogen. So 2-propanol is what we start off with. Okay, so that will have 2-propanol being converted into propanone and hydrogen will be at the highest rate at first. So let's have a look at to get rid of the destructors. Okay, so let's look at A. That has the opposite, propanone and hydrogen being converted into 2-propanol. The question says that 2-propanol is in the highest concentration, so this reaction will have to be the fastest. So we can remove A and C. Now B and D, they both have the forward reaction, or the one that we're looking at the highest rate and then decreasing over time. But let's look at how they differ. Over time, we have the rate decreasing because we decrease the concentration of our reactant, and the rate of the reverse reaction increasing because we're increasing the concentration of our product. Now, at equilibrium, we know that the rates of the forward and the reverse reaction have to be the same. So these ones are not the same. This is like a concentration graph, and I told you that they do it to confuse you, but we have rate on the y-axis, so it has to be D because they're the same. Now, only 40-something% of the state got that right. All right. Another example. Oops. Sorry. This example says that carbon monoxide and hydrogen can be produced from this reaction. Okay. Some methane and steam are placed in a closed container and allowed to react at a fixed temperature. The following graph shows the changing concentration of methane and carbon monoxide as the reaction progresses. They want you to write on the graph the changing concentration of hydrogen gas as the reaction progresses. Okay, so I've drawn that out here, the exact same thing. It's good if you have the question. Okay, so here we have the reaction, we have concentration, and then we have time. As you can see, the question said methane and steam are placed in a container, okay, and allowed to react at a fixed temperature. Now, so methane is at a particular concentration, doesn't have any values, but we know that it decreases by sort of 1 unit, okay, and carbon monoxide increases by 1 unit. This makes sense because if you look at the equation, we have a 1-to-1 ratio between methane and steam, and we produce a 1-to-1 ratio of carbon monoxide, and hydrogen gas is at a 1-to-3 ratio. So hydrogen gas is really the only thing that's not 1-to-1. So you don't need to know what this unit is, you just need to know that if I use up 1 unit of methane gas, I'm going to produce 1 unit of carbon monoxide and 3 units of hydrogen gas. So we have to ensure that the rate is the same, and we basically want to have an equilibrium concentration of 3 units from 0. So we increase it, and we get something like this. And we have to label it. So this should be H2 gas. Now the second question asks us to draw the line to show the formation of carbon monoxide in the presence of a catalyst. Okay, we have concentration over time. Basically, a catalyst will increase the rate of CO production. So in less time, we're going to have a higher concentration. So the curve should look something like this. We've seen this type of example before. But this black line is all you'd need to do, and labeling it as catalyst. Okay, let's move on to question number. Okay, question number 3 refers to calculating equilibrium constants for the reaction represented by the equation. If an equilibrium mixture of 3-litre container was found to have blah and blah, what is K? Now I told you we can work out K if we know the concentrations of our reactants and products at equilibrium. It says the concentration of N2O4, well, it says we know the moles of N2O4 equals 0.12, and we know the moles of NO2 equals equals 0.5. We know the volume of the container is 3 litres. We can easily work out the concentrations. Okay, so we can work out the concentrations. C equals N over V. So divide each by 3 will give us the equilibrium concentrations. Let me work that one out. O 0.04 M, and the other one is 0.5 divided by 3, 0.1667 M. Okay, so how can we work out K? Remember, keep this, in particular this value, in your calculator, and you can work out K from the equation should be, well, is NO2 squared divided by the concentration of N2O4 equals 0.1667 squared divided by 0.04, and it should be, so this is squared divided by 0.04, 0.69 to the correct number of significant figures, which is 2. Yeah, because 3.0 litre vessel. And let's see what the units of K would be. M squared divided by M. 2 minus 1 equals 1. So it should just be M. 0.69 M. This was question 7 from your textbook, so killing 2 birds with 1 stone. Let's just make sure it's correct, and it is. Okay. Next question. Question 8 from your books. The equilibrium constant for the reaction given by the equation blah 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 is 48.8. Okay, so I'm just going to start working it out. Just know that it's question 8 from your Heinemann textbook. Okay, so 2HI gas is converted into H2 gas plus I2 gas. K equals 48.8, and notice that K does not have units now because it would be M squared divided by M squared. They cancel out, that's why there's no units. So an equilibrium mixture in a 2.0 litre vessel at this temperature contains the concentration of H2, the moles of H2 equals 0.22, the moles of I2 equals 0.11, and the concentration of H2 and the concentration of I2 we can easily work out to be 0.22 divided by 2 equals 0.11. And equals 0.055 M. Now, that's all well and good. We need to calculate the concentration of HI at this temperature. We can do that from the K constant. So that should be H2 I2 divided by HI squared equals 0.11 times 0.055 divided by HI squared. So 48.8 equals 0.00605 divided by HI squared. Okay, so how can I bring it on this side? Well, you can just do it times by HI squared. Cross those out. 48.8 equals 0.00605. Oops. Okay. Divide it by 48.8. So HI squared equals 0.00012m. Take the square root of that. The concentration of HI should be 0.011m. Significant figures. The mixture was prepared by placing 4 moles of HI in a 2-litre vessel at 330 degrees Celsius. At equilibrium, 0.44 mole of H2 and 0.44 mole of I2 were present. Calculate the value of the equilibrium constant at this temperature. So different temperature, K changes. So I just do my table, okay, which is 2HI, and then we have H2 plus I2. Then I have initial, 4 moles of HI, 4 mole, and then I have change, and then I have equilibrium mole and equilibrium concentration. Okay, let's work it out. So 4 moles of HI, what else do we know? 0.44 moles of H2 at equilibrium. And how many moles of I2? Exactly the same. That makes sense because it's 1 to 1. So how much of H2 will have to be the same as I2. Now how can we work out the concentration? We divide it by volume. So we have 0.22 m and 0.22 m. So this should really be in that. Okay, so then we can work out. Initial, you can fill those out if you want, not really necessary. So change. Now, we have to ask a question. If we started off at 0, okay, mole of H2, there must have been a change of 0.44 mole. That means a certain amount of HI was used to produce 0.44 mole, and we use stoichiometry to determine that. So 0.44, okay, the moles of HI equals 2 over 1, unknown over known, of the moles of H2 equals 2 times 0.44 equals 0.88. So the moles that we used is 0.88. So in other words, negative 0.88. This is positive 0.44, also positive 0.44. Nearly there. So the equilibrium moles will have to be initial minus change equals 4 minus 0.88 equals 3.12 mole at equilibrium. The concentration would be divided by 2, which is 1.56 m. Now we can just sub everything in to our equilibrium constant to determine K. Okay, so HI equals 0.22 times 0.22 divided by 1.56 squared. Okay, So you can go 0.22 times 0.22 divided by answer squared equals 0.020. Let's quickly check if that's right. Excellent. Okay. Now C. A third mixture consisted of 1 mole of HI, 0.24 mole of H2, and 0.32 mole of I2 in a 2-litre container at 330 degrees Celsius. Now they want you to find out, is it at equilibrium? Now we can simply convert everything into concentration. So the concentration of HI equals 1 over 2. Concentration of H2 equals 0.24 over 2. And the concentration of I2 equals 0.32 over 2. Now we can simply sub it into that equation for K, and we can work it out to see if it's at equilibrium. Now, we have 0.12 times 0.16 divided by 0.5 squared. Let's work that out. Oops. 0.0768. So our K is supposed to be 0.02. We have a larger K, which means we have more products than necessary. So in other words, we need to go backwards. This will cause a net back reaction. Backward reaction. Yep, okay, we got that right. All right, next one. Question is the one that we're moving on to. Okay, so I'm just going to work it out, but make sure you have the question in front of you. Okay. Write an expression for K. Easy. Let's see. So K equals H2O, concentration of H2O, times the concentration of CH3OCH3, oops, divided by CH3OH squared. See if we got that right. Excellent. 79% of the state got that right. Okay. Now, B. That's A. B. Calculate the value of K at 330 degrees for the following reaction. So it says the K for this is 5.74, and the reaction is 2CH3OH produces CH3OCH3 plus H2O. Now it's asking you, what is the K for CH3OCH3 plus H2O produces 2CH3OH. Now this one's pretty simple. What we have to do is work out, basically we're inversing K. Basically what we're going to do is K will be CH3OH squared divided by CH3OCH3 plus H2O. And can you see what we've just flipped it over? Or in other words, we've done 1 divided by this. So K would have to be 1 divided by K2 would have to be 1 divided by K1 equals 1 over 5.74. As I said, when you reverse the reaction, you have to do the inverse. Equals, and to 3 significant figures, 0.174. Does it have any value? No, because it's m squared divided by m times m equals m squared divided by m squared. They cancel out. So, answer. And 69% of the state got that right. Okay, C. C. Methanol is pumped into an empty 20-litre vessel. At equilibrium, the vessel contains 0.34 mole of methanol. Sorry. So the mole of CH3OH equals 0.34 mole. Okay? Calculate the concentration of methanol in moles per litre at equilibrium. Very easy. C equals N over V equals 0.34 divided by 20. .017 mole per litre. So let's do part C. CI we worked out to be 0.17 mole per litre. Now CII, calculate the amount in mole of dimethyl ether present at equilibrium. Okay, that's quite simple because it says that we start off with methanol, only methanol. So let's just look at our reaction. Only methanol was introduced into the reaction chamber. Okay, only methanol was produced in the reaction chamber. So every mole of methanol, which is converted into dimethyl ether, will be also converted into the same amount of mole of H2O. So in other words, at equilibrium, the concentration of dimethyl ether will equal the concentration of H2O. Okay, so with our reaction constant, we have 5.74 equals H2O times the concentration of H2O times that, and because they're the same, we can just say X times X equals X squared divided by, so X squared divided by CH3OH squared. 5.74 equals X squared divided by 0.017 squared. Simply solve. Times X squared equals this, square root of this, .0407. Sorry. N equals CV times V would be 20 equals 0.815 mole. And this is to the correct sig figs. Now for 3, let me just make sure you're focused. So that is the answer to that. Now for part 3, Can you see? Okay, for 3, we have to calculate the amount in mole of methanol initially pumped. So we know the amount in mole of methanol at equilibrium equals 0.34. Now the amount of mole of methanol, if we produce 0.81, and this was of dimethyl ether, how much methanol was needed initially to produce 0.815 mole of dimethyl ether? Well, we can just use stoic. 2 times the mole of methanol would be used to produce that. So the mole of methanol equals 2/1 times the mole of dimethyl ether equals 2 times 0.815 equals 1.63 mole. Now the mole of CH3OH initial equals the mole at each mole used. It's like back to the one we did before. 1.63 plus 0.34 equals, and to 3 significant figures, 1. Let me just make sure that I've got it right. Yes, 970 mole.